Okay, good morning everyone. My name is Mahmoud Kadkhodaei, and today I'm going to talk about shape memory alloys, a specific kind of smart materials. And I'm coming from Iran, as Professor Dalizola mentioned, and here I would like to first briefly describe where I'm coming from. I'm coming from Iran. In this map you see that approximately we are around 5,000 kilometers away from Italy, of course depending on what city we are coming. We are from Isfahan or Isfahan. Historically, you may know the name because after the Second World War, Iran and Poland has had several collaborations after your refugees, and Isfahan was one of the main cities who hosted most of the Polish soldiers and other civilians from there. Isfahan is somehow located in the middle of Iran, so I'm somehow coming from the middle of the Middle East. Here is a map of country. The country resembles a cat. You can recognize the head here. This is why cat is a symbol of our country. Isfahan has been the capital of the country during several periods of time. This is why Isfahan is referred to as the cultural capital of Iran, although Tehran and other cities nowadays the capital. This is one of the ancient squares called Naqsh Jahan. Somehow literally means the landscape of the whole globe, because several palaces and several mosques are here. This is inside the square, and it's a very historical place in Isfahan because several periods of time these palaces have been used for several kingdom purposes. Isfahan University of Technology was established in 1974 and officially began admitting the students in 1977. At present, we have nearly 10,000 students, among them near 30 or 7,500 undergraduate students. Nearly 500 faculty members in 11 engineering departments and 3 sciences departments, together with several research centers. Department of Mechanical Engineering was one of the first departments of the university. At the beginning of establishing the university, we had a department called Energy Department, containing departments of Mechanical Engineering, Chemical Engineering, and Electrical Engineering. And after that, we separately have different divisions and departments. In our department, we have nearly 1,000 students, 800 undergraduate students. Currently, we have 39 tenure-track faculty members, together with other adjunct professor and professor emeriti. We have 4 different divisions: applied mechanics, mostly concentrated on solid mechanics and the related materials. Another one is mechatronics and dynamic systems. The other division is manufacturing. We work on both traditional manufacturing processes and advanced manufacturing. And the last one is thermofluids. These are the 4 official divisions of the department. My talk today is related to introduction to shape memory alloys and some of their basic applications. I introduce some of our research works and achievements in the department, followed by some concluding remarks. We have a specific kind of materials called smart materials. Smart materials are smart. Why? Because they can have responses to different stimuli from different fields: electrical, mechanical, acoustic, magnetic, and so on. And shape memory alloys is one of the most recent ones. They have the memory of shape. How? If you look at this spring after permanent deformation, by heating we can recover its initial configuration. This is why we call it shape memory effect. Heating can be directly induced this way or can be induced by electric heating called Joule heating. For example, here, through electric current, we can recover the original configuration of the whole specimen. Sometimes shape memory effect spontaneously occurs. We call it pseudo elasticity or super elasticity. This is an orthodontic arch wire. You may have seen it. It's super elastic, meaning that after imposing nearly 9% deformation like this, without any external stimuli, we can recover the original shape. This is why we call it super elasticity, because it can recover a very large amount of residual strains. Sometimes we can induce magnetic field to recover the original shape. This is an animation by Adaptamat, a famous factory in Finland. By imposing magnetic field, I can obtain mechanical strain, large strains, compared to ordinary, for example, piezoelectric or piezomagnetic materials. And by using magnetic field, I can change mechanical responses in terms of stress and strain to magnetic responses. So, what's the origin of shape memory effect? We have thermoelastic martensitic transformation in a shape memory alloy, meaning that we have martensitic transformation, but despite martensitic transformation in steel, for example, we have thermoelastic transformation, meaning that it's reversible. The material has two stable phases. Austenite, which is high temperature, high symmetry phase of the material, and martensite, which is low temperature, low symmetry state of the material. In the course of cooling, the material begins to convert from austenite to martensite. In the temperature, say, martensite star, and the transformation will finish in martensite final. Upon heating, a reverse transformation occurs, meaning that martensite begins to transform to austenite, and austenite start temperature, AS, and then it becomes completely austenitic and AF. These four temperatures are the main specifics of an alloy. However, below MF, when the material is completely martensitic, if I induce stress, I can achieve macroscopic strain. During heating and cooling, no considerable macroscopic strain is achieved. But for this kind of martensite, upon the application of some external loading, I can achieve a strain. Both of these phases are martensite. But due to several reasons, we call this state twinned or temperature induced or multiple variant, because one of these reorientations are called one variant. Sometimes we call it self-accommodated, because in the absence of any external strain, it can be accommodated in the original shape. Sometimes we call it randomly oriented, because the orientations of the crystals are randomly distributed in the material. And sometimes we call it unbiased, because no specific, no biased direction is assumed for the orientation of one or other variants. In contrary, we call this stressed martensite detwinned, stress-induced, deformed, single variant, because all the variants are oriented parallelly. And sometimes we call it oriented martensite, biased. Accordingly, in a shape memory alloy, I have two stable phases, austenite and martensite. And for martensite, I can have two states, twinned, undeformed, and detwinned, stressed, deformed. Now I can explain what's happening in shape memory effect. In shape memory effect, I will begin with a martensitic state of the material which is stress-free, which is twin martensite. In the course of loading, detwining takes place because the material is being under stress. When detwining is completed, upon unloading, like ordinary materials, I can see some remained residual strain. But this is the main feature. Upon heating, the material cannot be remained stable martensitic at higher temperature. It has to be transformed to austenite, and austenite was high symmetry phase of the material. This is why all the induced residual strain are recovered and the material regains its original deformation. In super elasticity, the material should be initially at a high enough temperature, say above AF, so that the material is initially completely austenitic. During loading, again, austenite has to be converted to martensite. Which kind of martensite? Between martensite, because it is stressed. However, because in high temperatures, austenite is the stable phase of the material, upon unloading, the material spontaneously recovers to austenite and recovers all the induced strains. The loading path is different from that of unloading, meaning that some dissipation occurs in this hysteresis area, and this induces further properties of a shape memory alloy. This phenomena was first observed by Buller in 1961 in the Naval Ordnance Laboratory in the United States, and they were working on one of the first alloys in this year, nickel titanium. And due to this name, the alloy was further called nitinol. Nitinol is still one of the most applicable shape memory alloys. The first commercial application of nitinol was quick connectors, pipe couplings in F-14 fighter aircraft. Now, I can review again the properties. For instance, the shape memory effect. This is a shape memory alloy specimen, and if we severely deform it, you can look it. This is first describing nickel and titanium. You see, after very severe deformations like this, compared to original configuration, or for example this spring, I then induce this kind of severe deformation. When I put them on a heating plate, they begin transforming to initial state. This is called memory. The spring. In hot water, due to convection, transformation is rapidly. You see, very rapidly. Another property of these alloys is that the Young modulus, the stiffness of austenite, is different from that of martensite. Meaning that by applying heating, I can gradually change the stiffness of the material. You see? Austenite is stiffer than martensite. I hang a dead load, a constant load, to a martensitic shape memory specimen. It deforms. Upon heating, it transforms to austenite and recover the induced strains. More and more, by inducing heavier loads, I can repeat the same cycle and obtain shape memory effect. This means that the alloy is simultaneously acting as a sensor and actuator. It senses temperature and simultaneously reacts. Anyway, I prefer to stop this. If I use electric current by switching on and off, I can actuate something like this. On, off. On, off. Meaning that, for example, in a robotic R, instead of ordinary motors and heavy actuators, I can use a very thin shape memory alloy wire, and with the use of electric current, I can actuate different parts of a robot. Nowadays, shape memory alloys are called solutions looking for problems because they have potentially different properties to be achieved, and we can think about different tricks to obtain these properties. You see? Another side properties of these main characteristics. One of them is high power to weight ratio. I'm bringing an order, 10 megajoule per cubic meter. It is a very high number compared to, for example, hydraulic cylinders and other ordinary actuators. This means that we can use them in microelectromechanical systems, in MEMS, so that we can achieve very high forces and actuations in very small sizes. We have some stress plateau. If you look at the typical stress strain, no considerable strain hardening occurs in the response of the material. This stress plateau is more sensitive to temperature than the extent of strain. This means that in a variety of different applied strains, I can have almost constant stress. And I will explain the benefits in biomedicine and biomedical applications. Energy dissipation, I call them. They are inherently dampers. I can put them in some parts of some building and can apply them as some inherent dampings. I briefly talked about tunable stiffness. Since austenite and martensite have different stiffnesses, by adjusting the level of stress, strain, and applied temperature, I can tune the stiffness of the whole structure, and this is beneficial. Biocompatibility. Fortunately, a wide range of shape memory alloys, more specifically nickel titanium based and copper based, are biocompatible. And nowadays in the industry, in orthopedic, in several areas of medicine, shape memory alloys are commercially applied. In shape memory alloys which are titanium based, they are very corrosion resistive because titanium is a very corrosion resistant element. So, due to these phenomena, I can have some typical applications like self-healing. Since the material tends to obtain its initial configuration, here you can gradually see that by heating, it's gradually obtaining its deformation, the first configuration. I'm not sure if the video is correctly playing. Yeah, here. I don't know why Yeah. For example, a crack is induced in the material. I can use some SMA staples near the cracks, and upon heating, I can close the crack. Heat engine. This is one of our samples in our laboratory. This system containing shape memory alloy wire and two pulleys are spontaneously rotating. How? Here we have hot water, and the material is initially martensitic. When we put this part inside the hot water, it transfers to austenite, it retracted, and begins rotation of the pulley. We can use these alloys in energy harvesters. For example, we can use some waste heat to convert to applicable mechanical energy. This is called heat engine. Metallic tires. This is a prototype made by NASA. The struts are made from super elastic alloys. And you can see that they are very, very flexible compared to most of the ordinary materials. Super elastic behavior of the shape memory. Anyway, I prefer to stop it. Morphing aircraft. Another project by NASA. More or less, we know that birds can adjust their orientation and other directions of their wings. We can think about such a phenomenon in a real case airplane. So that in every mode of the flight, we can adjust, drag, lift, and of course increase maneuverability of a plane. This movie is describing the phenomenon. By electric actuation of some shape memory alloy tendons, we can actuate the flaps so that the wing is somehow working like those of the birds. These are several tendons actuated by electric current. Even shape memory textiles. A very short clip. I can embed some shape memory alloy wire in this cloth, for example, and think about textiles with memory. I can think about super elastic textiles so that the produced cloth can be easily fit to any size of the body because it's super elastic. Even artistic application. This metallic flower works with electric current. Electric current, again, actuates the material, causes transformation to its parent phase, its austenitic phase, and by switching off, it returns to another configuration. Here you can see a very flexible eyeglass frame. This is not just due to ease of usage. This is due to the stress plateau. Since the temperature of our body is almost constant, for different sizes of a face in ordinary materials, by changing the applied strain, I will obtain different levels of stress. But with the use of shape memory alloy, since I mentioned that the level of stress is more related to the amount of temperature rather than strain, it causes to apply almost the same level of stress. In robotics, I briefly mentioned, all the actuations here are made by electric current. No motor, no ordinary actuation. All by electric actuation of the SMA wires. Active vibration. Why? Because I can use a shape memory wire with tunable stiffness. Accordingly, with the use of electric actuation, I can tune stiffness of the embedded part inside the structure. You can see here an experimental setup. A beam is vibrating. Inside this beam there are some SMA wires. Control on, meaning that electric current on. You see that the amplitude is reduced because the stiffness of the material is changed. Even by disturbance, they can recover its original shape. I prefer to go faster. In the industry, these endophiles, you can see, by putting hot water, they can reshape. In the root canal of the teeth, which is a very complicated canal, I can use these endophiles with a less chance of rupture. And this is very beneficial for a dentist. For orthodontic arch wires. Arch wires are used to reorient the malfunctioned teeth, you may know. I can follow the configuration of the teeth in the hope that I can obtain this ordered shape. I put martensitic sample inside the teeth, and upon heating with no external actuation, just when the material gains the temperature of the body, it begins recovering its initial shape. In endoscopy and colonoscopy, this is a colonoscopy capsule inside which a shape memory alloy actuator is inserted, and by electric current I can actuate the capsule. Here is the description of the phenomena, and you can see that just by electric actuation the capsule is moving inside the canal. Anyway, so what we are doing in our department, since 2004 we have been involved in several projects related to shape memory alloys. I can divide our research in three different categories. The first one is characterization. Characterization in terms of obtaining thermal, mechanical, thermomechanical properties of these alloys is somehow challenging. The second part is constitutive modeling, how to develop a reliable model so that the model is able to predict several behaviors of the shape memory system. And of course, design and manufacture of several smart devices. And I will explain these things. First, characterization of thermal parameters of a shape memory alloy includes obtaining transformation temperatures, the 4 transformation temperatures I talked about, specific heat of the alloy, and transformation latent heat. One technique is called DSC, differential scanning calorimetry. I put a very small size specimen of the alloy in some pan and induce heating and then cooling, and I can obtain such a schematic response, heat flow in terms of temperature, for example, heating and cooling. In the course of heating, for example, I can see an almost horizontal line. At the onset of transformation, a peak is occurring and then it reduces to the same horizontal line, and the same phenomena are seen during cooling. With the use of these simple equations, I can realize that these lines are useful to obtain a specific heat of the material. These areas, integral of the response, yields total latent heat, enthalpy of the phase transformation. And of course, I can obtain the 4 transformation temperatures. Another techniques are in need of in situ measurements. In the course of loading or heating the sample, I should measure electric resistance of the material. You may know that electric resistance is somehow a linear function of temperature. In the course of transformation, we have some deviations between the two lines, and hereby I can obtain or estimate transformation temperatures. Sometimes we can induce a dead load, and in the course of heating and cooling, by changing the observed strain in terms of the varying temperature, we can obtain the estimated values of transformation temperatures. These measurements are done in parallel to confirm measurements of any technique we have been formerly used. Combination of thermal and mechanical properties is related to Clausius-Clapeyron relationship. This relationship says that when we are converting from a stable phase of the material to another stable phase of the material, P, the applied pressure, T, the induced temperature, this quantity is related to lambda, the latent heat of transformation, instantaneous temperature of the material, and change in the whole volume of the body of the material. Using this relationship, and after several experiments by conducted, for example, simple tensile tests in different temperature range, we can obtain this stress temperature phase diagram. This phase diagram is somehow like a map. In the space of stress and temperature, this diagram tells us which state of the material is stable. For example, here I have austenite as a stable phase. Here I have temperature-induced martensite. Here I have stress-induced martensite. Between these areas, I have transient areas between, for example, austenite to stress-induced martensite, and so on. By conducting simple tensile tests or sometimes compression tests like this, we can obtain maximum recoverable strain of the alloy, the Young's moduli, and other properties so that we can construct such a phase diagram. This phase diagram contains this strip, this, and this. This is one of the typical phase diagrams of a shape memory alloy. In our observations, we realize that we should think about generalization of this typical phase diagram, at least by changing the considered slopes of this strip, or for example, for both the strips. You can see the response. If I wish to use the typical phase diagram, I cannot easily resemble the experimentally verified response. The dashed lines are numerical simulations with the use of ordinary phase diagram. But if I use these generalized phase diagrams, I can obtain a more reliable response. Although I can briefly talk about three-dimensional constitutive modeling. I prefer to concentrate on one-dimensional constitutive modeling. We have to consider two internal variables in a shape memory alloy. One of them is stress-induced Martensite volume fraction as temperature-induced Martensite volume fraction. Summation of these two yields the total Martensite volume fraction inside the body. Think about a simple decomposition of a strain. We can have elastic strain and transformation strain, which is related to maximum recoverable strain of the material and stress induced of the total Martensite. Why just stress induced? Because remember that temperature induced Martensite was not accompanied by any macroscopic strain. Young modulus, as I mentioned, is not constant, but rather depends on the total Martensite volume fraction of the material. In terms of this relationship or other relationships which are governed by simple relationships which are developed for composite materials. For different parts of such a phase diagram, we have to develop some evolution rules governing change in the amount of Martensite volume fraction. I'm just bringing one of these relationships. The main point is that temperature of a shape memory alloy is not constant in the course of a loading-unloading cycle. Why? Because the transformation is inherently endothermal or exothermal. Why? Because the applied stress power can stimulate the endothermal or exothermal nature of the material. This is why if I capture temperature of the alloy, sometimes you can see that very increased temperature occurs in the course of loading, and then temperature decrease is observed in the course of unloading. I have to consider these variations when modeling a shape memory alloy. To do this, we have developed a one-dimensional fully coupled thermomechanical model by considering this helpful free energy, elastic, thermoelastic. This is due to transformation, and this is just implying the thermal effects. And with the use of the first law of thermodynamics, or energy conservation, I can obtain, for example, in this response, variations of temperature at different strain rates for different sizes, for example, for one wire. Since temperature of the material is simultaneously varied in the course of loading and unloading, stress also varied in response to the applied strain. This is why in response to several applied strain rates, I can obtain several levels of stresses for a constant level of strain. Another side effect is that maybe I can begin loading on a shape memory alloy whose temperature is initially more than AF. It's initially austenitic. But after unloading, the temperature is below AF. It's no longer austenitic. You can see that although temperature is more than AF, I would see some residual strain. These details are required to be considered when designing a smart device with the use of shape memory alloy. Another phenomenon which can be observed with the use of this model is transformation-induced creep and relaxation in these alloys. For example, here you can see loading, and during loading the temperature is rising. If I stop the applied strain, since the material begins cooling, the level of stress is reduced. In a reverse sense, in the course of unloading, the material is going to have a smaller value of temperature. If I stop loading, the material regains temperature and increase the level of stress. In terms of creep, if I induce strain during the intervals, strain is increasing. When I stop the applied stress, strain does not remain constant, but varies. Why? Because temperature is varying. These all defects cause different responses from one cycle to another cycle during cyclic loading of shape memory alloys. Fortunately, we will obtain a stabilized cycle, and this phenomenon you may know is called shakedown. After obtaining the stabilized response, the material is somehow trained, and we can now easily use the trained alloy. When training, I will face different temperatures of the alloy. Accordingly, I have to consider a cycle-dependent phase diagram. Why? Because temperature is simultaneously varied. We have developed some models in which the quantities inside the phase diagram are explicitly expressed in terms of the applied, for example, strain rate, number of the cycle, and so on. Even we can estimate number of the stabilized cycle before simulating the response. For example, in such a loading, number of the stabilized cycle is 13. And before simulating all the 3 cycles, I can obtain with the use of these relationships. N stabilized is 12.5, meaning that is almost equal to 13. We can use this approach to predict the lifetime under fatigue. It's been proved that in the course of fatigue loading, dissipated energy in the stabilized cycle governs the value of the number of cycles to fracture of the material. Alpha and beta are material parameters. This relationship helps us to predict fatigue life before rupture, before fracture of the material. Meaning that in the initial stage of the loading, when shakedown is achieved, I can obtain the observed dissipated energy. And with the use of this relationship, I can predict life cycle, number of cycles to fracture, in terms of, for example, minimum stress, maximum stress, and frequency of the applied loading. In our numerical simulations, we have at most 9% error, which is reasonable to predict life cycle of a shape memory alloy. We have extended this approach for axial loading, rotary bending, and torsion. This is the experimental setup for rotary bending. This resembles the endodontic file I talked about. We first bend the material, then we turn on the motors. The material is rotating while it's been bent before initiation of the rotation. If you look at the phase diagram is believed to be independent of the initial phase of the material. But we show that this is not the case. Like hardening in ordinary materials, if in point B, for example, I induce an elastic interruption and begin reloading, initiation of the transformation is point B, not point A. You know? Even in DSC, in the course of heating and cooling, if I interrupt the heating in the course of transformation, meaning that in partial transformation I revert the heating or cooling cycle, I would obtain a different value of transformation temperature. This means that transformation temperatures are fixed number only and only if I induce complete transformation. During cyclic loadings, I may face some partial transformation. Therefore, I should develop a model to be able to predict the changed value of transformation temperatures in the course of incomplete transformations. We introduced the concept of transformation surface instead of transformation phase diagram. A three-dimensional surface in which the initial value of Martensite volume fraction is playing a role. You can see that, for example, compared to experimental results, if I arrest temperature, meaning that I induce some incomplete transformation, 45 degrees, for example, the subsequent start temperature is 45.6, and our prediction is 45. As I interrupt the transformation in 42, experimental observation is 42.4, and our prediction is 42. If I interrupt the transformation at this temperature, all the results are the same. You can see that this way I can predict the so-called strain hardening. So we can extend these models to predict interfacial debonding in SMA composites. In one of the clips, I showed a beam inside which some SMA wires were embedded. We can think about delamination of the wire inside the whole structure. Here is an experimental setup so that we embed a wire inside a matrix, and we can develop some interfacial models so that the model can predict the debonding force in different wire lengths. We have developed three-dimensional models. I didn't go through details, and we are now able to predict behaviors of porous and cellular shape memory alloys. In such materials, material asymmetry occurs, meaning that tension and compression of the material do not have the same material parameters. Moreover, plasticity occurs inside the materials. By considering these effects and the idea of unit cell in a repetitive style of a 3D printed specimen, we can predict behaviors of a 3D printed shape memory alloy. We can use our approach in vibration analysis of a semi-reinforced composite beam. Like the movie you watched, if I consider some wires inside a beam, I can obtain decrease in the amplitude of vibration when switching on the electric current. We have observed some local deformations in SMA specimens. You can see here that transformation starts very close to one of the grippers in our experimental setup, and propagation of phase front, initiation of second phase front can be seen in the results. Macroscopically, we can see some stress drop when localization occurs, and we have used non-local constitutive modeling to predict such behaviors. So the last part of my speech is related to some instruments we have developed with the use of shape memory alloys, and of course using our models. The first one was a temperature control unit for flat solar collectors. Sun cannot be switched off. This is a big challenge. This is why if I design a thermal chamber, a thermal collector, for example, for winter days, I will face some difficulties during summer because superheating occurs. In ordinary tricks, we use some ventilation valves so that the heated fluid can be discharged. Here, we propose a valve, we call it thermal valve or adaptive valve, a smart valve, so that if you consider the collector plate, an absorber plate, just attached to absorber plate, we attach some SMA wires. These are sensors of temperature. When temperature reaches to a critical value, elongation of the wire activates this valve, and some opening occurs in the whole box of the collector. Free convection with the air induces cooling, and then when temperature reaches to another critical value, the valve is automatically closed and regaining heating is occurring. You can see here the valve opening with temperature. The dashed lines are our numerical predictions, and these spots are experimental findings. For example, we were planning to completely open the valve at 120 degrees, and experiments showed that nearly 140 degrees the valve is completely operated. This device was commercialized by the Ministry of Mining in Iran. Another idea is called killing damper. A damper with no viscous fluid, with no ordinary damping components. We just use the dissipation I talked about in the course of a pseudo-elastic cycle of a shape memory alloy. This is the schematic structure of the damper, and this is the constructed damper. We use SMA tendons together with a bias spring. Bias spring meaning that the spring is made of ordinary materials, no shape memory effect is seen in the spring, and we can see such a response in terms of force displacement, in tension and compression of the whole damping setup. Let me bring you some examples, some numerical values. If I consider this definition for the equivalent damping ratio, WD is the area of this area, and these values are related to stiffness of the bias spring and deflection of the whole structure. The achieved equivalent damping is 12%, while the inherent damping of a lone wire is 7%. We have had some sort of similar devices with the use of shape memory alloys. Our achieved damping ratio is nearly 45% more than the most recent SMA dampers. Another thing is shape setting to produce some predefined configurations of a shape memory alloy. Consider that I'm gonna produce some shape memory spring by using shape memory wire. If the shape memory wire is austenitic, it means that when I put it in a helix, by removing the shaping tool, it will recover its initial shape. So I cannot produce a spring. If the initial wire is martensitic, it means that after producing the spring, upon hitting, I can recover the initial shape. So what should I do? I should take some actions called shape setting, meaning that with the combination of heat treatment, cold work, and the quenching of the heated sample, I can induce some specific configuration in the shape of a specimen. For example, you can see such a spring here made from some wire. And memory is now attributed to the shape of the spring, not the shape of a straight wire. Again, our models can predict with reasonable accuracy the force displacement response of the spring. Why we are thinking about the spring? Because spring is more easily applicable under compression. We cannot easily apply nitinol wire, for example, or SMA wire under compression. We are currently working on 4D printing, meaning that 3D printing with the use of shape memory alloys and of course shape memory polymers. This is one of the points we are thinking about some collaboration with M&MoCS. We can think about producing some pantographic structures with the use of shape memory polymers so that we can extend the level of the formations and we can recover the induced formations in the pantographic structure when the material is shape memory polymer. We are developing some specimens for energy harvesting. I showed you one of the experimental samples called heat engine, and we are now developing those ideas to produce some industrial energy harvesters so that in industries we can use the wasted heat to produce a portion of required power. Now we are in need of investigating multi-axial fatigue because multi-axial fatigue contains several complicated phenomena, including responses in non-proportional loading. When the loading is non-proportional, we will face some complications. I didn't talk about these values. The research group at present has one undergrad student working on shape memory alloys. We have 7 master students and 3 PhD students working on this area. So far we have graduated 12 Bachelor of Science students, 33 master students, 4 PhD students working on shape memory alloys. These are our international collaborators with our research group. We have an MOU with France, with IACDL and ENI. With the University of Toledo in the United States, we have some collaborations. And hopefully we are working some collaborations with M&MoCS for the printing and other areas in terms of shape memory alloys. And SMA, an acronym for shape memory alloy, I think about single to married alloy, because so far 4 couples have been working in our group, and it seems that working in shape memory alloys induce some romantic behaviors in some ones, because it seems that our group is productive in this way too. So, thank you for your attention, and hope you enjoy it.
Thanks a lot for this.
Thank you.